This video is going to explore some probability concepts, and there's a couple vocabulary words that you need to be familiar with. So the first one is a trial, which is one repetition of the experiment. Then we have the sample space, which is the set of all possible outcomes of the experiment. And then finally, the theoretical probability, which is the probability of an event occurring. And for event A, we can use the formula. The probability of event A is equal to the number of ways A can occur divided by the number of items in the sample space. So number of ways A can occur divided by the number of items in the sample space, which is also your number of possible outcomes. Okay, so let's look at an example of applying this. You want to show all the possible outcomes from tossing a coin 3 times in a row, and then we're going to list the theoretical probability of each outcome. So if we have a coin toss, we can either get a head or a tail on the first flip. Same thing on the second flip, a head or a tail. And finally, same thing on the third flip, a head or tail. And following these branches is going to give us our possible outcomes. So if I follow the first branch of the tree, I've got heads, heads, heads. And then I will switch to blue for the second branch, head, head, tail. And I can continue all the way down the tree here. So then I've got head, tail, head, head, whoops, tail, 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 head, head, tail, head, tail, 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 head, and finally tail, tail, tail. So then we'll list our probability based on number of heads. That's the way we'll organize that. So the first way we can look at it is the probability that we get 0 heads. So I'm going to count my total number of outcomes. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to count the number of ways that I can get 0 heads. Well, that is only one way right here. So that means 1 outcome out of 8, I'm going to get no heads. So that would be my probability. The next one I'm going to look at is how often do I get 1 head? So it's going to be out of 8 again. And then I'm going to circle all the outcomes where I only have 1 head. So 1, 2, 3 possibilities out of 8. And then I'm going to do the same thing for probability where I have 2 heads. So again, it will be out of 8. And I've got 1, 2, 3. And then the last one is going to be the probability where I get 3 heads. That is my only remaining possibility here. So just 1 out of a possible 8. So a couple of things you should notice. One is that my probability of any particular event is always going to be between 0 and 1. And if I add up all of those probabilities, I'm going to get a total of 1, which you should. anytime you've calculated the experimental probability or theoretical probability for the outcome of all your events, when you add them together, they should add up to 1. The next example that we're going to look at is rolling dice. And many board games involve rolling 2 6-sided dice. We are going to find the probability of rolling a total of 11 with 2 dice. The first thing that we're going to do is set up a dice roll chart in order to help us count the probability, the total number of possibilities that we can get 11. So here, my first one, I can roll a 1 on my first dice and a 1 on the second, a 2 and a 1, a 3 and a 1, or a 4 and a 1, and I can keep filling them in here. So this is a useful chart to memorize or redraw every time, because a lot of the probability examples that we're going to look at involve counting sums or outcomes on 2 pairs of dice, or it could help you when you are playing board games with your friends and family. Maybe it will give you a slight advantage to be able to calculate the probability of rolling a particular sum of numbers. So 5, 2, 6, 6, 2. Okay. So now I've got all my possibilities listed here for rolling 2 dice, and I'm going to count how many times I get a sum of 11. Well, that is only these 2 possibilities here, where I roll a 6 and a 5, or a 5 and then a 6. So that means that my probability of getting a total of 11 is my number of outcomes that give me 11 over the total number of outcomes from rolling 2 dice. So which would be 36 possibilities, which would give me a total probability of 1 over 18. The last example that we're going to look at uses something called the complement probability. Sometimes it's easier to count the events that don't satisfy your criteria than it is to calculate the events that do satisfy your criteria. This is similar to our idea of the number of elements in set A plus the number of elements that are not in set A has to equal our total number of elements that are in the sample space. So the example that we're going to look at here to illustrate this property is using perfect squares. We're going to find the probability that one randomly drawn integer between 1 and 49 inclusive is not a perfect square. So we know that there are lots of numbers that are not perfect squares, so it's going to be easier to count the number of items that are perfect squares in that range. Because of the complement probability, I know that the numbers that are not perfect squares plus the numbers that are perfect squares has to add up to 1. So I'll leave my not perfect squares here. And I'm going to move my probability that it is a perfect square over onto the other side, just using algebra. And then I'm going to figure out the probability that the number is a perfect square. So I've got 49 options to choose from. Only 7 of those are going to be perfect squares. So let's list them. So we've got 1, 4, 9, 16, 25, 36, and 49. So 7 numbers, which means that 42 out of 49 times, I'm going to choose a number that is not a perfect square. So I can further reduce that and say that my probability that one randomly drawn integer is not a perfect square is 6 out of 7. So an example of using the complement property along with the examples of some of our other probability concepts that we're going to discuss in this unit.